questions. So each question was 10. So this is basically average about 14 questions correct. That's pretty good. Okay, let's move on to the lecture. Let me turn my video off.
This meeting is being recorded.
Lecture 11 and 12. Okay, so that's the agenda for placement. Okay, let's move on to lecture number 9, which cover the placement part 1. So these are the topics that I'll be covering for the placement. First, just an introduction of what is placements, and then followed by the placement objectives. What are the objectives in placement? And then we move on to inputs. What are the inputs? And then the placement steps, which divided into 3 different areas: pre-placement, placements, and post-placements. In each one of these steps, there are sub-steps also. And then after placement, we'll discuss congestion analysis, basically cover what is congestions, and then how to analyze congestions. So if you have congestions, how do you fix, how do you minimize them, which will lead us to the next topic, guides to minimize congestions. And then we move on to the outputs. What are the output placements? This one is good. Okay, so here's the overview of the placement flow within the 3 steps. So in the pre-placement, we'll discuss about sanity checks. Okay, so if sanity check is good, we move on. Basically, this is checking the result from floor plan.
This meeting is being recorded. This meeting is being recorded.
Each of the technology in ASIC, they will define a site, which is equal to a minimum width and height of a standard cell. Okay, so in the technology left, there'll be a site definition like this. It'll be site core and class called core, and then symmetry is X and Y. So the size X is 0.2 micron, the height is 12. So this is the width of the site here, 0.2 and the height is 12. Okay, so a cell can take up multiple cells. For example, here you can see a cell that take up 4 sites. Right? But in a more advanced geometry, like 4 or 5 micron, you can have multiple site definition. You can have this is a core. You have additional site definition core 2 that can have different heights because the library to accommodate different cell heights. So that can happen. Okay, so what is a row? A row is also defined as technology library. It has constant height. The height is actually dictated by the row because the row is actually dictated by the site because the site actually make up the row. So here you can see a row, and then within the row there are a whole bunch of sites, right? Make up of sites. So same thing, it can have a different heights because of different site definition in the low geometries, right? So this is an area where the standard cell plays, obviously, right? So row can have different orientations also. You can have Rx, MX, and so on. So here the example, this is the bottom row, very bottom is R0 is denoted by this, and it's a flip and a butted here. And the same is repeated. Here also different orientation, bottom MX, and then flip and butted. Okay, and same thing here. But this configuration called double back rows is where there's no channel between back to back to back. This is the most popular row layout in current version. These have channels because in older technology, there's a limited number of metal for routings, so they need to space out so that they have resource for routing between. But these are most popular these days in current geometry. Okay, so here it's just in a double back. This is the double back. So you can see VDD is shared between the rows, this row and this row, and then VSS is shared between these 2 rows. So continuous like that, the rest of the core. Okay, so let's discuss about legal standard cell placement orientations. There are 4 possible legal orientation of standard cell placement. So the first one is R0, which is denoted by this lower left corner. So this is considered R0 orientations. Okay, so you take this and you flip, you mirror against the y-axis, you get this orientation, that's why they call it MY, stand for mirror on the y-axis. Okay, and then you take R0, you flip it on the x-axis, you get this orientations, which is called MX, right? And then the last legal orientation is called R180s. You take this R0, you rotate 90, and then another 90, which is 180, and you get this orientations. That's why they call it R180s. So these are the 4 legal standard cell orientations. So if the cell happened to be global placed incorrectly or flipped incorrectly, it'll get flagged during placement check. Okay, any questions so far?
Nothing in the chat so far?
Okay. All right, let's move on to the next slide then. Okay, so this slide basically just show you, this is before placement, there's no standard cell in the row, and then after placement, there's standard cells in the row. So there's okay. Let's talk about another terminology, a concept that is very important to placements. It's called placement densities. So density is the amount of space used for placement of standard cell out of total space. Okay, so within density, there's two terminologies. One is cell density, the other is core density. They're a little bit different. So cell density is defined as the total area of standard cells, all the standard cells in the design, divided by the total placeable area in design. So for example, take this area, assuming this is the entire design. So this is the total standard cell area, the black I'm pointing to here is the total. And then you take the total area of each standard cell add together, divided by the total available placement area. That's going to be the cell density. So the core density is the entire, including the macro here, right? The total placement area. Okay, so you take the total cells and the macro divided by this total area is called the core density. So basically everything within the core area, including the macros, is called the core density. Okay. So in practical, in my experience, is that if the placement density is more than 70%, it's going to be difficult to route. Okay. There are some technology and some type of designs, the placement is only 50%. So it varies depending on technology and design also. But anything I've seen larger than 70, it'd be difficult. Okay. So higher density usually lead to congestions, and we'll talk about congestions later. So here you can see, you zoom in here, you can see that I circle here. This area is higher density compared to this area here. So you see there's less cell, there's more space between. So you may ask, why do we have higher density area versus lower density? Why the tools just spread out evenly? Well, that's because it depends on the placement strategy. Okay, so it depends on the timing requirements, congestion requirements, and connectivities of all these cells. That's why the way it's placed. But we, as an engineer, we can control upfront, and we know there's certain areas congested or not, we can control and spread these out upfront to prevent it from clustering or having higher density, which then lead to congestion routable design, which is not what we want. Okay, I hope this makes sense. If not, feel free to ask questions. I tend to go fast, but you can try to slow down. Okay, let's move on to the next slide. So the other important concept is routing tracks. Okay, so routing track defined as a predefined path that router must use to route net and connect cells. Okay, so basically if a technology has 14 different routing layers, and then there will be 14 different routing tracks assigned to those layers. Okay, and they can be horizontal or vertical tracks. Okay, so you can see here is a vertical track, there's horizontal tracks, right? So there's terminology sometimes called preferred directions versus non-preferred. So a preferred directions basically mean that a vertical track here, preferred direction is vertical, and the horizontal direction for the track will be a non-preferred. Okay, so sometimes you hear a term non-preferred route or non-preferred direction route. Basically, this picture depicts. So this is we have a route here in a horizontal direction, which is preferred direction, and they take a jog in a non-preferred direction because this metal here, let's say this metal 2 is horizontal, and it jogged down and go another metal 2. So it actually took a vertical while the preferred direction is horizontal. So this refers to a non-preferred directional route. This happened very rarely. I mean, maybe less than 1% of the time that the route does that, because what happened is if it does cross 2 track, then you wasted the entire track right here, the horizontal track. So sometimes it does that to avoid shorts. So that's what's called non-preferred directional non-preferred routes.
So,
Okay,
but
so
there are a couple of questions.
okay.
So first, why placement density should be less than 70%?
Okay, so in my experience, most of because higher than that, in most of the technology I've seen, higher than that is there's going to be is too dense to route. There's lack of routing resource. So, for example, in the most recent one I did, the density of some of the blocks only 50%. So it dictated by the design type and the technology, but I haven't seen anything that over 70 that in my experience that's routable. And Phil, Ting, you have any additional answers for them?
But
Yeah.
yes, I think mostly the technology, right? We routinely, route the design with upper 80%, right? So like 85%. So, but our design is not like 3 nano or 5 nano, right? So we like 22. So
I see.
when you when you get to the lower, then certainly you get the lower density. So I think the answer should be, just dependent on the design, right? And it's not a fixed number, right?
Yeah. So it's like I said, design dependent, technology dependent, but in my experience, I haven't seen anything over 80. I mean, over 70 is routable. I guess most of the design work is on a lower nodes. Yeah.
Yeah, I'd like to add a couple of things. Another factor would be the number of routing layers that available.
Sure.
So the more routing layers, the more density you can get, right? For example, if you at 70 and you have 5 layers of metals to route and you route cleanly, if you use 6 or 7, you might be able to increase 70 to 75, for example. So that's another trade-off, because if you use more layers to route, it's more costly. So you usually just the task of the physical designer is to do analysis and see where the sweet spot is in terms of number of layers to use for routing. So is a function of cost versus density, right? So another thing I like to add is the quality of the standard cell placement area also affects the density that you can get. The most efficient one will be the square and big contiguous area, like but show in the previous slide. That one you can get high density, but if your standard cell placements is rectilinear, meaning it's not the big rectangle, but it's more like an L shape, Z shape, and it turns and twists, then you wouldn't be able to get very high density. So another factor is how you floor plan it, how you place the macros in such a way that your standard cell areas is not fragmented and is contiguous. So those are things I would like to add.
Yeah, that's a good point. Thank you, Phil and Ting.
So there's another question. What is the command to show the density in the picture?
You use check in Innovus check text underscore floor plan dash report density. Okay, so yeah, I'll have it in a minute. In one of my slides, I have the command. I believe is checks underscore floor plan dash report density. So we'll get to that in a minute. Yeah, I'll have it on the slide. Okay. All right. Thank you. Anything else before we move on to the next slide?
Yeah, there's another one from Nguyễn Văn Trung. The more layers, the higher cut. Is there any principle or tip for choosing the number of metal of layers?
Yeah, so I got the reason the higher cost because the more mass set, right? Usually in the design, it's really by the time we get it, by the time that our teams get it, it's already dictate how many layers we get. But from the standpoint, we it's how do you call it? It's calculations, right? Based upon the technology, the cost. So it's a whole bunch of factor come in. The cost per die, and then the uh, the cost per die, and then the number of die they sell, and so on. So they calculate overall and they determine the ROI, the return on investment. So, for example, if you can do a design that is in a 12 by 12 millimeters in 12 layers, and it costs you X amount, versus you can do a 12 by 12 in less number of layers, cost you less. They'll do in a less number of layers. So does that make sense?
Yeah. Also, like Bud said, sometimes when it goes through the physical, the digital place and route people, the number of layers already determined by all the calculations dictated by the analog design, for example.
Yep.
But the question relates to if really the digital guy is going to determine the number of layers versus cost, then you would go you would know in the foundry or a standard cells vendors, they typically have a number, the dense what do you call the density numbers that you can refer to, say number of gauge per square millimeter or something like that. So you use that as a guidance, and also there's no simple principle other than just you just have a very good experiment, and the power grid has a lot of influence on how dense you can get. So that will be design dependent. If your design consume a lot of power, you need more resources for your power grid. Therefore, you need more layers underneath to achieve your density. Your density target. So there's no principle other than understanding your design and understanding and do the different factors that influence it, and good test cases, and go through the analysis yourself, and you can feed back to the team, and the if you say, hey, I'm really having a hard time, with a number of with the number of medals that you given me, and this is, say, I'm getting only 50%. I'm requesting 2 more, and this is what I'm going to get, and have them go and calculate all these different cost functions, and then they will come back and say, this is what makes sense economically, right? So.
If I can add to that, as a system architect, part of my job is working with technology team to involve in determine the metal stack for each of new technology node that we want to implement our product. So some of the factor that drive the decision on how many metal layer that we will select. Let me give you an example. For example, the 22 nanometer technology node, like from GlobalFoundries, there are multiple metal layer options that we can choose from. The factor that drive the decision at whether the chips will include embedded MRAM or embedded RRAM, resistive RAM. Those will add additional layer. If the chip includes radio frequency, like to design like Wi-Fi or Bluetooth type product, those will also add additional metal layer. And even for the mmWave, meaning that you design a chip with 24 gigahertz or higher frequency for 5G or 6G Wi-Fi. That's also another factor to try for the additional metal layer. So it comes back to the what type of product are you going to build, you going to design, that will decide the number of metal stacked.
Okay, thank you, Volk. Yeah, I mean, in reality, is when you join a company or a team, they have history of these technology or similar chips that they can derive these things from. Okay, so if it's brand new technology, then they would have study and know exactly, like Phil said, you know, density per millimeter square, and that's will be the base on where they go on. Okay, so I think the other thing I want to show here, you can see the track here. You see how the routers actually use a track to route these on metal 1 and metal 3, and then metal 1 and metal 2, metal 3. So that's in Innovus, you can actually turn on the track and see what's happening here. Okay, let's move on to the next topic. Thank Phil Vo and Ting for chiming in and answering questions. Okay, so the next important topics in placement is placement blockage. So there are 3 different type of placement blockages: hard, partial, and soft. And these are the, you know, understand these well and know where to place them will help you quite a bit in resolving a lot of your congestions during placements. Okay, what is hard blockage? It is, once you define this is hard blockage. When you find this, there's no cell that's allowed within this area. Okay, you may ask, why the heck do you want that? Okay, so there are certain area where, for example, in front of like macros, a lot of pins coming in on the lower layers, you don't want any standard cell to be placed there, because you place there, take up a routing resource where it may be congestion in front of that. So that's where you use this to block off the entire or the area where you don't want any cells to get in. Okay. So next is the partial placement blockage. So partial is basically you allow the cells inside, all the cells inside, but not to exceed a specific number of percentage or placement density. So for example, here we create a partial density. So basically saying that you can place cells in here, any cells in here, but the density may not exceed 50%. Okay, so this is some of the strategy that you know, if there's an area that's going to be very dense, you want to control this. If naturally the tool may place it exceeded, 50 or whatever number it is, you want to control to a specific number. This is where you want to apply this partial blockage. Okay, so here's a partial blockage. You can see around is a lot of cells, and then with this partial blockage, the cells are limited to less dense. Density will be lower. Okay, and this is the picture show the hard blockage. So with hard blockage, no cells in there, all the cells placed around it. Okay, last, what's called soft blockage. So soft blockage is used during the IPO in-place optimization or optimization. Only buffers, inverters are allowed within. Okay, it's only used during the optimization for setup, hold, timing fix, DRV, and so on. And also that the percentage not to exceed what you specify. So for example, this is the sub blockage with 25%. Okay, so why do you want to use this? So sometimes you have, let's say, memories, right? Have a lot of pins that are placed in between channels. You don't want any cells in here because you want to use that area to allow buffer to drive long signal coming in. So that there's the routing source is really rare here. So you want to reserve that for the time engines to insert buffers and inverters to fix whether DRVs or timings. So that's when you want to use this stop blockage. Okay. Okay, so next, let's talk about the floor plan objectives. So these are the objectives that placement objectives. Sorry. So first foremost is to meet timing, area, and power requirements, and then to minimize congestions, and then placement density. Also minimize or fix all the DRVs, which is max transits, max capacity, and fast fan out. Okay, we'll talk about these in the next few slides. Bottom line is, after placement, you want a routable design. Okay, meaning that minimum congestions, also meeting timings and power and area requirements. So these are objective for placement. Okay, so what are the inputs for placement? A net list, a physical left, a def, and a MMC multi-mode. This is basically it contains your libraries, constraints, and RC corners. And if it's low power, it needs UPF. So basically, this information contained in the floor plan DB. So if you run NFS, you finish floor planning, just save the DB as floor plan, and then read it import it into placements step. So that's in reality, that's what happened. Okay, so this is listing what are the things that are actually in there. Okay, so these are the placement step within the three sub-step of placements. So in pre-placement, we send sanity checks, and then in placement, we're in global route, global placement, detail placement, high fairness instances, do scanning, DRV fixing. And in post-placement is where we start fixing timings, power area ops, tax insertion, add spare, MBFF optimization. This is just a quick introduction to MBFF. It stands for multi-bit flip-flops. And then we do congestion analysis, and then also we'll talk about how to minimize congestions. Okay, so in pre-placements, we do a quick sanity checks. What do we check there? So once the design came out of floor plan, right, we want to make sure that all the IOs, port pins are placed in their proper location and fixed. Okay, so by the time it came out, everything, all the IOs and pins should be fixed. And also all the macros and, and memories should be placed and fixed with the proper halos and placement blockers around them. And all rows are created correctly. And then the other important thing is stripes and so on that was created in floor plan need to be short freeze. And you probably ask, okay, there's a lot of checks you got to do, but you know, the tool will have some of these built-in commands that actually will help you to check these. So here is the Infos log and some of the commands that actually can run to check. So to check the floor plan, to do sanity check, you do check underscore check floor plans. Actually, it's check underscore happened, but anyway, check underscore plan is actually will check some of these things that we just discussed, right? Routing tracks, fence and regions, and so on, and overlaps and whatnot in the macros. Okay, and the other one you can run and check DRC, check shorts only, which will check all the shorts to make sure that the pound ground PG that was created in floor plan to be short freeze. So came back with 0, then we're good to go. Okay, and there are some other things that so here example here it said one of the halo should be created around this block, this RAM block. So it give you a warning. It doesn't necessarily give you an error by default. It's a warning. So you have to review this warning, make sure that it is something that you need to be fixed, right? So you need to review all the log file. Okay, so in placements, there are 3 different strategies that you can do. Basically, this is how you want to drive the placement engines as a primary targets. So the first one is timing-driven placement, which is most often used. Is also the default strategy in Innovus. So if you don't do anything, it's going to run a timing-driven placement. So primary goal in timing-driven placement is to meet timing, obviously, right? And how does it meet timing? So the algorithm is basically trying to minimize, reduce the wire length between two device or two cells that communicate to each other. For example, here, right? You get D and G talk to each other. The shorter distance is next to each other. This is route. This is the shorter distance, right? Versus the congestions, right? The congestion goal is primarily to minimize congestion. So here example here. So D and G is actually spread out. D and G here spread out, and in this placement is actually congestion driven here. You move it apart where there's no congestion, right? Less congestion. It's like 3 track. There's only 2. Right? So in congestion, primary is to spread out cells and reduce congestions, right? And in either one of these, so in timing-driven placement, the primary goal is meeting timing, but it's still going to try to meet the other target like congestion and power, right? But it's secondary to timing, right? That's what you said. Likewise, in congestion, the primary is to meet congestion, but the tool is still trying to meet timing and power target. But if once it's trying to meet timing and create congestion, it's going to back out because this is your primary goal in this strategy. So the third is power-driven placement. So primary goal here is to minimize power consumptions. So basically, it's going to employ clock gatings and also reduce leakage power, right? Change different cell type to reduce power. And again, same thing. Timing and congestion is going to be also optimized, but it's going to be not as high as probably is in this power-driven placement. Okay, so in Innovus, these are pretty much the command that will set it. By default, this is already set high. So in congestion is you want to change congestion after high. And then likewise in power. Okay. Any questions, comments? And Phil, Tang, you guys have any additional inputs?
No, I think you covered well. Yep.
Yeah, just one additional note, as you mentioned that halos are just warning, meaning that in practice, a lot of times we don't use halos. So you would probably go without halos first, and if the design is routable, then yeah, you don't need halos.
Pretty much if the block is just around the macros. Okay, so yeah. Okay, let's move on to the next slide.
There are a couple of questions.
Okay.
I'm jumping in, Dave. Sorry to take over your job, but before we go on the next topic, so Vũ Quang Minh asks, so we use just one or multiple strategies at once?
You use one primary, right? So you have to tell the tool which is your primary goals, but the tool still is going to work on the other 2. For example, by default you use timing-driven placement, right? That's your primary goal. So the tool needs to know the primary goals, and then the other 2 you still have constraints, right? As far as power target and congestion target. So it will one goal, but it's still going to try to do the other 2. It does not ignore the other 2 targets at all. But the primary target will be 1. Does that make sense?
Yeah. And some addition to that is that keep in mind when you keep everything high, if you have a huge design that has an impact on runtime. For example, if your design takes 3 days to finish the placement, now you put everything high, it might take a week or 2 or whatever. So that's one thing. So there's a trade-off between runtime and what you want out of these runs. And another thing is that if you put everything high, then the design, the tool might have harder time achieving your primary goal of timing, for example. So
Yeah, it's best to only have one primary goals, right? Only one. Yeah, so you don't confuse the engine.
so that's another